Today, let's talk about how mathematicians ingeniously depict real-world phenomena. If you want to draw a perfectly smooth curve with mathematical formulas, it has to be flawlessly sleek at every single point. This is what we call an analytical solution, exquisite and crystal-like. Yet such ideal forms barely exist in reality. Turbulent typhoon currents, shock waves around aircraft, fractured geological faults, derivatives break down in these scenarios, and no perfect formula can fully describe them. So how do we tackle this dilemma? Mathematicians came up with two powerful practical tools: Sobolev space and weak solution. Let's start with Sobolev space. Picture a vast meadow. We don't demand every blade of grass to be impeccable. Instead, the overall total energy stays finite and stable, and the average gradient remains controllable. Minor pits and steep slopes are acceptable locally, as long as the whole landscape follows general rules. This type of functional space that prioritizes overall order while tolerating local imperfections is named after Soviet mathematician Sergei Sobolev. Back in the 1930s, he noticed traditional mathematics was overly rigid and incapable of solving practical physical problems. He then established this mathematical space, allowing functions to contain discontinuities, while still maintaining overall regularity. Most natural states of fluids, solids, electromagnetic fields, and gravitational fields fall within the scope of Sobolev space. They run smoothly in general, with occasional abnormal changes. Based on this theoretical framework, weak solutions come into play. A weak solution does not require equations to hold true strictly at every point. It only needs to comply with fundamental laws such as energy conservation and momentum conservation in an overall average sense. It accommodates abrupt boundaries like shock waves and fractures, and still delivers accurate descriptions of physical reality. From a macroscopic perspective, all possible functions reside in an endless dimensional space. Analytical solutions are rare elite dwellers living in luxurious palaces, pristine yet detached from reality. By contrast, weak solutions in Sobolev space are like ordinary residents in regular neighborhoods. Communities abide by universal rules, and minor individual differences are permitted, mirroring the authentic nature of the world. Thanks to Sobolev space and weak solution theory, scientists can simulate typhoons, design aircraft, explore black holes, and forecast earthquakes with computers. Modern mathematics no longer chases only flawless, ideal models. It embraces imperfect, tangible, real existence instead. This is the true brilliance of contemporary mathematics. It perceives and interprets our complex real world with wisdom and tolerance.